Okay, so this is the last part of this unit on field theory. That's a very small part, so let us quickly do this. And it's a very simple part also, so I hope you can pick it up very easily. So this is about ruler and compass constructions. Okay. So if you remember during school, you must have done in geometry constructions using ruler and compass. That is exactly what this is. No difference. Okay. But you can see now that ruler and compass constructions are not just simple-minded constructions. They also have some deeper algebraic meaning to it. Okay. So that is what we will see. So some of the very basic ruler and compass constructions I will actually not even cover because that is something that we know from school days and we have done it many times. So very basic ruler and compass constructions, I won't do it. I will straight away jump to what are called constructible numbers. Okay. So quickly let us revise the basic rules. So we are allowed to have an unmarked ruler. Okay. A ruler or a scale without any marking and a compass. Okay. Now you all know what a compass is. Okay. Now assume that we are given R2 along with the X and Y axis. Okay. We are given this much, right? And the origin 0, 0 is marked. Okay. The origin is marked. Right. Now the unit length is fixed arbitrarily. How do you do that? Well, X and Y axis are given, right? So on the positive X axis to the right side of the origin, just make some marking and fix that to be length 1. It doesn't have to be centimeter, meter. There are no units here. Okay, just a measure of length. Make an arbitrary marking on the positive x-axis. That will be defined as your unit length. Okay, that point will have the coordinates 1, 0 because it is on the x-axis. And then similarly, you can take that same length with a compass. You can make the same marking on the y-axis also. And so 0, 1 coordinate is also marked. Now, do you realize once you mark unit length, you can repeat this again and again by changing the center of the compass and go on marking all integer coordinates, right? So you can mark every other point 2, 0, 3, 0, 4, 0, and so on the x-axis. Similarly, you can mark 0, 2, 0, 3, 0, 4 on the y-axis by just repeating. The center of the compass, you first placed it at the origin. Now you place it at the next point, then the next point, then the next point. You can keep doing that. So the integral vectors on the x and y axis are very easy to mark. Okay. So that was the very basic stuff. Now, before I go ahead, okay, there are some extremely simple ruler compass constructions which you did in school, okay, which you should revise. Okay, so it is given in a PDF. So if you remember, for some of our proofs, we were using a PDF proof1.pdf. Okay, so this is another file which I will upload in MS Teams. This is proofs2.pdf. Okay, proof2.pdf, page number 3, end of page number 3. Okay, forget everything else. There are many other complicated ruler compass constructions which are given here. You don't have to bother about any of these things. Okay, this is more advanced stuff. We are not doing that. We are only looking at basic ruler compass constructions. So straight away go to page number 3, and in page number 3, at the end, you will have this line called standard constructions. These are the standard constructions which you did during school. Okay, so just revise them. Okay, so what are these standard constructions? Given a line segment, how will you bisect it? Okay, how will you find the midpoint and bisect that line segment? So the construction looks like this. Okay, I'm not going to explain, read through this. You have done this in school, so I'm not going to repeat this. Okay, very simple. Then the next one, bisection of an angle. Given an angle, how will you bisect the angle? Right, now the construction there looks like this, the final diagram. Once again, just go through this. You have done this in school, very easy. Okay, so just read this and revise. You have done this already, so I just want you to revise. The third one is drawing a right angle. Okay, given a point, given a line, how do you draw a right angle to that? Okay, that is a construction. Drawing a perpendicular. You are given a line and you are given a point outside the line. how do you drop a perpendicular from the point to that line? Remember, these things you have done. So that is another construction. Drawing a parallel line. You are given a line and a point that is outside the line. How will you draw a line that is parallel to the given line and passing through the point? Okay, so suppose L is a constructible line. Forget the word constructible here. What it really means is you can get these by ruler compass constructions. That is the only meaning of it. Okay, so L is a line and P is a point outside the line. How will you draw a perpendicular from the point P to the line L? Okay, so these are extremely basic 5 simple constructions. What are these? Quickly, how do you bisect the line segment? Okay, how do you bisect an angle? How do you draw a right angle? How do you drop a perpendicular from a point to a line on which the point is outside the line? And how do you draw a parallel line? Given a line and a point outside, how do you draw a parallel line passing through that point? Okay, so these are basic ruler compass constructions. Just read through this and whatever is written here, try to repeat it. In fact, you don't even have to read this. If you just start playing with your ruler and compass, you might even remember this on your own, how you did this. Okay, so very, very simple. Then there are remaining parts about algebraic properties of constructible real numbers and etc. 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 You don't have to look at any of these things. Okay, what we need, we'll just do it very simply in today's lecture. Okay, if you want, feel free to read this, but I think what we do in the lecture is enough. Okay, so from this PDF, all you have to do is look at the standard constructions. Okay, the standard constructions. That's all. That starts at the bottom of page 3. All right, so that is proof. This file proof2.pdf, and we are done with this. Let's come here. Okay. So what do we mean by constructibility? Okay, so we say a real number is constructible if the absolute value mod a. Okay, a is a real number. Now construction, essentially these numbers should be available as length of some line segment. That is the idea. So there is no separate meaning to constructing a negative number. We say a negative number is constructible if the corresponding positive number is constructible. That is a definition. Okay, so a real number a is constructible if the positive part, if mod a can be obtained as a length of a line segment obtained via some ruler and compass construction. Does not matter what. Via some ruler compass construction, if you can obtain mod a as a length of a line segment, then that number a is constructible. This is about real numbers, and we say complex number a plus ib is constructible if both real and imaginary parts are separately constructible. That is the definition. Okay, so a plus ib is constructible if a and b are both constructible as real numbers. That's all. That's all the basic definition. And now the main thing here is that the set of all constructible numbers actually forms a field. Okay, so what does it mean to say set of all constructible numbers? So for us, script C will denote the set of all constructible numbers, and we will consider this to be the set of all constructible complex numbers. Okay, but for simplicity, we will just prove this for real numbers. For complex numbers, it will follow immediately because of this property. The real and imaginary parts are independently constructible, so the complex numbers are also constructible. Okay, so we will prove some properties of constructible numbers only for real constructible numbers. What is that? So if a is constructible, script C is the set of constructible numbers, and we are assuming that we are working with real numbers. So if a is constructible, then minus a is constructible. That is obvious. There is nothing to do here because by definition, a is constructible if mod a is constructible. So minus a should also be constructible. Then if a and b are two constructible numbers, the sum is constructible, a plus b. If a and b are constructible numbers, the product a times b is constructible. If a and b are constructible numbers and b is non-zero, then a by b is constructible. Okay, so do you see this set is closed under addition, taking negation, taking products, and taking division, right? So this is a field. That is the main thing. Okay. So trivially, by what I just said earlier, by marking points on the x and y axis, we clearly have that set of all integers is constructible, because if you can mark unit length, you can mark any integer length by the same idea, by repetition. So integers are all constructible, and then the set of constructible numbers is a field. Okay, so if integers are constructible and if C is a field, then fractions of integers are also constructible by this property, last property. So the whole set of rational numbers is constructible. Okay, every rational number is constructible, and therefore C is a field, and it is contained between the set of rational numbers and the set of complex numbers. It's between Q and C. Okay, so the set of all constructible complex numbers is a subfield of C, and it contains the set of all rational numbers. If you only consider real constructible numbers, then the set of all real constructible numbers will be a subfield of R, and it will again contain all rational numbers. Okay, that is the main proposition here. That's the only theorem that we have to learn here, and the proof is just this, proving these properties. Okay, so how do we prove these properties? So I have written here, as we have seen in video lectures, that is this lecture. Okay, so I will show now how to prove these things. Okay, so let us do that. All right, so let us first prove. So A is constructible implies minus A is constructible. That is easy. I mean, that follows by definition. So let us prove the second one. Let's prove that if A, B are constructible, then A plus B is constructible. Okay, that is also very easy. Why is that? So let's consider the x and y axis as usual. Okay, and for simplicity, you can check the other cases. They are in fact much easier. Okay, I'll just prove it for positive numbers. Okay, but it is much easier. I mean, it's the same argument. You can try to repeat it. Okay, so let us take a point here. 1 second. Okay, this should work. Okay, I have taken a point here. And I have taken another point here. Okay, there are 2 points, and I am not concerned with the order. And without loss of generality, let us assume these are the points A and B, where A is less than B. Okay. Now, how will you construct A plus B? Right? It's extremely easy. So, do you see? This is the origin, right? Now, from the origin, I can take a compass and measure the distance to the point A. Okay, don't move the compass. Place the compass center at the origin, measure the distance to the point A. Now don't change the compass, just lift the compass, place the center at B. Okay, place the center at B and draw the arc with that same distance. You see, so that distance is what? From the origin, you measured distance to A, which is A itself. The distance is equal to A because this is from the origin. Now the same distance, when you draw it as an arc, okay, from B, it will add distance A to B on the right hand side. So when you mark the compass here, when you make the arc, it will be B plus the distance A, which is B plus A, or A plus B. Okay. So this is the point A plus B. And that's what. That is why A plus B is constructed, because you have A, you have B, you can measure the distances from the origin. Take the distance from origin to A, place the center of the compass at B, and take the same distance and that distance will add to b, right? So then the distance that you get will be b plus a or a plus b, and you can mark that. So therefore a plus b is constructible. Okay, that's all. Very, very simple. That is all. So a plus b is constructible. Okay, so save this. I will share these images with you later. Okay, that's what we have. Now let us clear this. Can you clear this directly? Okay, we'll have to erase. Fine. All right. Now let's do the new one. So once again, let us draw the axis, x-axis, y-axis, and that gives us the origin. Okay. Now we want to prove the next part. If a and b are constructible, then a times b is constructible, the product. All right. Okay. So how do we do that? So again, let's do the simple case. So again, I mark a on the x-axis. Okay. I mark the point a on the x-axis. Let me also mark the point b on the y-axis. Okay. So this time, the markings change. A is here. Let us say b is here. All right. These are the two lengths. Now what do I do? So now let me assume that b is less than 1. Okay. So then I'll also mark the unit length, the unit length that I have here. Okay, you can assume that b is less than 1. In fact, if b is greater than 1, it's a similar construction. Try that. Okay, it's a very similar construction. Try that on your own. Okay, so you should try it after you go back. Similar construction, these two will exchange. B will be above, 1 will be below, and that's all. But you can do the same construction again. Okay, so what do we do now? Join the line segment A to B here. Okay, join the line segment A to B. So this gives a triangle, right? Now this is a line segment, and the one on the y-axis is a point outside this line segment. So by the basic construction, okay, drawing a parallel line segment passing through a point outside, I can draw a parallel line here. Okay, parallel to the original line, and I make the marking that I get there. Okay, this point. Let's call this point X for the moment. Let's call this point X. Now, what is X? So, do you see this is a right angled triangle? Both, there are two triangles that you see here, the origin point A, point B, origin X and point 1. These are right angled triangles. So you can use similarity. Is that okay? Right. So by similarity, what do you get? So I can compare. Oh, I think I gave you the construction of division. Okay. Anyways, that's okay. So this is probably a division. Never mind. Okay. So by similarity, I can compare the two sides separately. Larger triangle to the smaller triangle. So x by a by similarity should be equal to b by 1. Sorry, 1 by b. Yeah, that was the difference. X by a is equal to 1 by b. Okay, by similarity, comparing the larger triangle with the smaller triangle. X by a is equal to 1 by b. But if you solve this, you move a to the other side, you'll then get this implies x is equal to a by b. Right? X is equal to a by b. So this is actually a by b. This x is actually equal to a by b. Okay, so sorry, I was not doing product, I was doing the division. Okay, so this is the construction for the division. If a and b are constructible, then a by b is constructible. All right. So just have a look at this and look at that ratio once again. Take a minute and see if you understand. All right. So this is fine. Now let me save this. So this is fraction. Okay. So if A and B are constructible, then A by B is constructible. Okay. Now for the product, it's a very, very similar construction. All right. So how do you do that? So now let me change this here itself so that let us change this figure a little bit. Okay. Minor. So the product and fraction proofs are not very different. Okay. So I change this. I don't have a point here yet. Okay. And I take out this line. And we don't have this fraction. We will do a new thing. Okay. The line stays as it is. Okay. So again, we are back to the same setup. We mark A on the x-axis and B on the y-axis, and let me again just assume without loss of generality that B is less than 1. When B is greater than 1, you can just flip it around and repeat the construction and check that it will still work. Okay, so that is like homework. Okay, the same thing. The only difference now that you do is that instead of joining A with B, join A with 1. Okay, join A with 1. Now this is a line segment and the point B on the y-axis is outside. So now draw a line segment parallel to this passing through B. So this is a line segment that is parallel, and let us do the mark. Okay. Now this is the point. This is the point X for us. Once again, just look at similarity. Okay. By similarity, what do you get? Now again, comparing the larger triangle with the smaller triangle. Yeah, comparing larger with smaller triangle, we get A by X is equal to 1 by B. Okay, it has been flipped, right? One of the fractions has flipped now. A by X is equal to 1 by B, comparing larger triangle with smaller triangle by similarity. What does this imply? Cross multiply, X goes above on the right side, B goes above on the left side. So cross multiplying, we get AB is equal to X. So X is equal to AB. Okay, so this is equal to the point AB. Okay, don't get confused. Why is AB less than A? Because B is less than 1. Okay, if B is greater than 1, then you will get AB on the right hand side of A. All right, that's it. So products and fractions are both constructible when the two numbers are constructible. So let me save this also. And that's it, we are done. So what have we proved? So by definition, negative numbers are constructible. If A and B are constructible, A plus B is constructible. If A and B are constructible, A times B is constructible. If A and B are constructible, B non-zero, then A by B is constructible. So all the field operations work. Okay. Therefore, the set of constructible numbers forms a field, and trivially it contains all integers. So the set of all constructible numbers is a field, and it contains the rationals and is contained inside complex numbers. Okay, so that is the main result here. Set of complex constructible numbers is a field, and Q contained in C contained in complex C. Similarly, if you look at only real constructible numbers, then even that is a field for the same reason, and you will get Q contained in C contained in R. That's all. Okay, so that's all about constructible numbers that we have for this course, and this completes unit 5. Okay, so I'll put up this video lecture also on the YouTube channel, and this is the full set of notes that you already have actually, which is already there on MS Teams. I'll just upload the construction diagrams also on MS Teams. Okay, and without fail, don't forget you have to go back and revise the basic constructions or standard constructions from the file proofs2.pdf. Okay? The standard 5 standard constructions. You have to revise that. And that is it. That completes. That completes this unit and also this course. So that is the end of this course. So thank you. Nice talk.